Right. It's about the time, so I will just get started. So in this session, I think you have already picked your particle successfully. If you did not, you don't need to be freaked out because you are doing great. And we have the recording and everything will be recorded. So you can go back to the recording to follow the steps we have just done like in your pace. So in this session, once you have picked your particles and how to get to the high resolution structures, and in this session, I'm gonna teach you how to get to high resolution structure. Okay. Uh, okay. So first, go to the workshop we just created, and first I will, while we are waiting for the pre-processing, um, I'm just like introduce what types of blocks and what are the types of refinement we need to do to get to high resolution and what's I'm going to demonstrate in this session. So as I introduced earlier yesterday, we need to do the reference-based refinement first to get the particle orientations, initial particle orientations, and it will take a lot of time because you can't search the parameters globally exhaustively, then followed by the fully constrained refinement to refine the two series alignment parameters and get rid of the bad particle in the particle filtering and refine the motions or model the motions during the data acquisitions using pad region-based refinement and do the masking to create a shape mask and do the region-based refinement using the shape map we just created and do the per particle CDF refinement. And because this data set's HIV wine gag protein has data movie frame, we are going to refine the movie frames motion, and then followed by our last one is the processing to sharpen your map. And this order for this data set is actually from, you can get access to the workflow and the tutorial. So I will just not, and we are going to demonstrate these blocks using a pre-run workflow. I'm gonna show you how to get access to that. But to simplify the processing, I'm just going to demonstrate the reference-based refinement with the pre-computing alignment parameters because doing the reference-based refinement from scratch taking a lot of time. And then followed by the particle filtering and create a mask based on the reconstruction we got from the reference-based refinement. And also I'm just to do some movie frame refinement without doing the alignment because it also takes some time. And then lastly would be the post-processing. So I'm gonna demonstrate this in this project, and I will demonstrate these blocks from the pre-run blocks. So first of all, that initiates the reference-based refinement from the pre-processing and using the pre-alignment parameters. So we only process one data set, so you don't need to be too like stressful. HIV1 get protein. So this one. And for the reference-based refinement, we are going to use the pre-alignment parameters, but there are so many settings I listed here. So first of all, you create a block from the pre-processing by clicking the blue icon in the bottom right, and it shows like particle refinement. Click on it. And the data set, for this data set, the molecular weight is 300 kilodaltons, and the particle radius is 150. And the symmetry of it is C6. Okay, and then move on to the extraction tab. In the tutorial, we are using binning 2, but now in order to speed up the process, I'm going to use for binning 4 to make the reconstruction smaller so everything will run faster. And the box size here is 96. And also turn off the skipping goal fiducial options. And for the refinement, the initial model, you can get access to that in the workshop. So click on it and then go to the 10164. there's like an initial reference.mrc. Click on it and choose the file. And then using the pre-alignment parameter, we also provide it in the same location. It will direct you to the previous block, but you just import that to go to the home page and then go to the workshop, same 10164. And just want to highlight, if you're are using Intel machine, which is looking at the URL, it's Barasaki Lab 09, you should use the Intel one. And if you're using 10, Note 10, which is you need to use the AMD one, which I'm going to use the AMD one for my instance here. It may not always work if you don't have the exact same number of particles, but it's fine. You can just look at me demonstrate the things. And then because we are not doing any kinds of refinement, we need to skip the refinement by clicking the skip refinement options under the refinement tab. Now we can go to constraint refinement because we are not doing any kinds of refinement and you don't want to select all of these options. And reconstructions, and you want to enable the advanced options and go to you will see the max tilt angles and the min tilt angle. Because this data set, you have some black images, they are not useful. Somewhere at the high tilt, maybe 60 or minus 60, you can get rid of them and only extract the particle extraction within, I would say, 50 to minus 50. You need to change that accordingly. So the tilted image beyond that range will be excluded. And yeah, we also want to enable the exposure weighting, and you can just leave the rest of it default. And for the resources, if you are using AMD, which is 10, Barasaki Lab 10, you should use 124 and maximize the memory, let's say 700 for the refinement process to make them run faster. And for the threads, it can be the same, like 3 threads and memory and 100 for the merge job. All right, so I think everything else set, just click on save and you will create a new block. That's how we create a block from the pre-processing. And then just click run and only select the block we just created and run the block. All right, and then I want to mention, if you are using the pre-alignment parameters, you need, for AMD, which is Barasaki Lab 10, you need to have this number of particles, 14,270. Otherwise, it won't work. You will see error message, and it's fine having like error message. You can just see me demonstrating things. And for the Intel one, Barasaki Lab 09, you should get 14,182. Is the exact same number for the pre-alignment parameter. And it's also fine if you do not have the same number of particle and something failed. You can just look at me. All right, while we are waiting, so we already covered how to create a new block, and we will see the result from the particle refinement block. So first, I'm just go ahead to create a new block while we are waiting, like a particle filtering block. You can click on it, even though you didn't get the result yet, you can still create a particle filtering block based on it. And for the particle filtering, we are going to use the value from our tutorial, which is 2.5 as the threshold and 10 as the distance cutoff. I mentioned yesterday the score threshold will be used to get rid of the bad particle that have lower scores. And for the mean distance is used to get rid of the particle, they are too close to each other. So otherwise we will see the positive correlation because of the duplicate particles. And the lowest, the input parameter, we will get it from the previous block once it is done. So we just leave it here. And for the lowest tilt angles, I'm going to use minus 15 to plus 15. So to calculate the per particle score, for each particle, we have multiple tilted projections. I just want to use the projection fall within this range for the per particle score calculation. And then we want to select the generate reconstruction after filtering. So that's save it for now until we get the result from the particle refinement block. And then I'm also going to demonstrate the other blocks we have, but we are not going to cover or demonstrate in this project. You can get access to the pre-run workflow from, let's go to our website for nextPYP, nextpyp.app. And you can go to the live demo and try the live demo. So you will see we already run these 3 datasets, which was also the tutorial datasets, and go to the 10164 GAG protein. So you can see all the processes and all the panel, all the blocks from the raw data to 3D structures. And so while we are still waiting, let's dive into the results first. So in this panel, in the particle refinement block, the same block we are running right now, we can see the slice of the reconstructions. You can see the unmasked FSC. If you have multiple iterations, you will see multiple curves. And you can also take a look at the orientation of the particle distribution and the defocus distributions, and they are in per particle projection basis. And go to the bottoms. You can also get the statistics from the refinement. You can get a better idea of the distribution of the rotations and also the defocus. Now this data set has 5 tail series, and you can kind of see there are 4 populations. And this score distributions and so on. And we also, I just mentioned the per particle score. You can get the per particle score in this panel by selecting the threshold in the particle filtering block. And you can download the map, and I will go into show you how to download the map when I'm going to demonstrate the RTIX. And go to the 3D view, and you can view the maps from the iterations, like different maps. You can put it side by side, make it larger, and compare the 2 structures. Now it's like same iteration, but usually we get the maps from different iteration and compare them. And you can superimpose them to see the structural difference in detail and adjust the threshold and just the level of detail. Some simple operation also provided in Chimera. Right. Okay, we are still waiting. So the particle filtering block, for the particle filtering, you should always see there is like a score. There's like a score distributions as well, but they are in the per tail series basis. And you can select the threshold based on the distributions. Usually, ideally, you should see 2 population in the histogram. You can select the threshold in between to get rid of the bad particle that falls that have lower score. That's the things I want to cover. Also, I thought I see a lot of question asking whether or not we have the tilt whether or not the tilt geometry or the tilt convention is detected. Yes, we do detect the tilted handedness. So you can get that information from the log of the pre-processing when we are estimating the CTF, and click on the log from the split job for this 10164 pre-processing block and scroll to the bottoms and go to the log. You should see the warning tab saying that the invert CTF handedness option should not be turned on, should not be selected during the refinement. And it's just a warning, it will not do it for you. So you have to go to the refinement block and go to the refinement tab or constraint refinement tab. There's like invert CTF handedness. And in this case, we do not want to select that because the CTF estimation say that we cannot, don't select this, right? Okay, so I think 1 till series is complete. And for the exposure weighting, as I mentioned yesterday, you will see that the weights used for the reconstruction in the exposure weight panel. And you can like make it larger. So the score, average score, if we plot this average score over the order of the acquisition, depends on your the tail scheme you use. It can be like sequential from -60 to +60, or dose symmetric starting from 0 degree and plus and -3 and plus and -6. In this case, it's dose symmetric. So the first few tilted image has the best quality, and it also has the better score. And the weights we use for the reconstructions is computing from the score we computed here. And the x-axis represents the frequency, y-axis is the cumulative weight. As I introduced yesterday, each band represents one tilde image that contributed to the high resolution. So usually I tune the two parameters, fraction and transition parameter, and see how it looks like for the weight. If I do not satisfy, I'm not satisfied with it, I will change the parameter for the exposure weighting accordingly and try it multiple times. Yeah, I think that I have get it. Okay. So I already introduced the this tab and exposure weight and the 3D view. All right, so we are going to go ahead to clean the particles. So we just create a new particle filtering block and click on Edit. Now we have the pre-alignment from the previous block. We want to go ahead. It will direct you automatically to the previous block, and you just click on it. And each file represents and alignment parameters. Just click on it, the one we just created, and then yeah, everything are all set. You click on Save and run the particle filtering. Don't forget to also provide a reference by clicking the reference and get the initial model from the previous block. Click on the reference we just reconstruct. Click Save and run it. Right. So now we have to be careful. Look at the log from the particle filtering block because it will tell us something while we are waiting. Right. So in the launch panel, it will tell you how many particles left using the criteria, using the distance cutoff and the threshold, and how much percentage of the particle are left, or how many particles are discarded. So in this case, using this set of parameters, 2.5 threshold as a threshold and 10 distance cutoff, we will get rid of about like 20% of the particles. And because we are selecting the generate reconstruction panels options, so we are going to reconstruct a new reconstructions or the map using the clean particle. So we have to wait until it is reconstructed. All right, so and go back to while we are waiting, go back to the demonstration, the pre-run workflow. Yeah. So I'm not going to demonstrate region-based refinement. So this is the place we do region-based refinement. And you can see the parameters are pretty much similar, and we do not do the binning here. And in our case, we used 4 just to speed up the process, but it doesn't really matter. So in order to do the region-based refinement, go to the constraint refinement tab, and there's like a number of regions. And now we have 8 by 8 by 2. So the number of region will be 8 times 8 times 2 in X and Y and Z dimension respectively. Usually we start with 2 by 2 by 1 and look at the map to see whether or not we see overfitting or everything makes sense, and then increase the number of the regions by the factor of 2 to 4 by 4 by 2. and then increase it to 8 by 8 by 2, etc. So these options, and then turn on these to refine the tilt series alignment parameters and refine the particle alignment parameters will allow you to refine using several patches to kind of model the local motions during the exposure or data acquisition. And the same as before, if you click on the particle refinement block, you should see the size of the map, FSC, just to check whether or not you get a good FSC. And also exposure weighting, they are pretty much the same thing. And you can see the map from different variation in 3D. Right. Okay, those almost done, but I will still keep going. So if we are going to do the per particle refinement, per particle CDF refinement, that is very simple to do. It is still done in particle refinement block. And go to the constraint refinement tab. There's like refine CDF per particle option. You just click on it and that's everything you need to do the per particle CDF block. And usually it is followed by region-based refinement. Right. So now I'm in the stage of the per particle CDF refinement. Go back to the particle filtering block. And we haven't yet done this. Still reconstructing the tomograms. And that's go back to the movie frame refinement. Even though we are, I'm going to demonstrate the movie frame refinement, but we can look at the thing we can get from the movie frame refinement block. Same as before, you can see the reconstructions, download the map, and you will get those things called particle view. Particle view is essentially because we need to apply some kind of regularization on the movie, on the trajectory of the movie frames. You can use it to visualize how the trajectory looks like on the 0 degree, and each trajectory represents the trajectory of the one part for each particle. And in this case, you have multiple particles. You can see it whether or not the trajectory are similar compared to the neighbor. If they do not look similar, you can tune the parameters for the movie frame refinement. And exposure weight, they looks totally different from the weight we computed using per tilt score. It will have more data point because each data score represents the per frame score instead of per tilt score, and the same parameter may not produce the same weights we use for the reconstruction because they will be more granularly. Each band represent one tilt image. So I will demonstrate how to tune the parameter just to show the result first. And we do have, you can see view the 3D models or 3D reconstruction in this tab as well. Okay, let's go back to the previous block. We can see we use fewer particle because we are kind of using the threshold in the particle filtering. So there are fewer particles. And you can still go to that tab to see the reconstruction. Usually, if you have the duplicate particle, there's like positive correlation. Now it's in a very high level of binning, you cannot see it. But if you go to the high resolution frequency, you see a positive correlation. That means you have duplicate particle. You can use it to check whether or not the duplicate particle are actually discarded. Let's go back to it. And then I want to introduce a new options in the particle filtering block called permanently remove bad particles. So if you do not select this option, the bad particle in the downstream process will be still extracted, which is not useful. So in order to get rid of them permanently, we need to select these options to get rid of the particle. So the bad particle will not be extracted, will not be used during the downstream process to speed up the process. And I just simply click run. And this process should be pretty fast. While we are waiting, we can create a new movie frame refinement block. So let's go to the movie frame. Okay, first we want to create a shape mask. shape max, the prerequisite for the shape max, we can create it based on this. From the reference space refinement, click on the icon in the bottom right. There's like a masking, create a masking block, and select the reconstruction you want to use it to create the shape mask. In this case, the MRC file, choose it, and the threshold. I will show you how to determine the threshold, but yeah, we can just leave it there. Some arbitrary values, and the width of the cosine edge, we are going to use 8 here. And how to determine the threshold? Go to the particle refinement block, and we go to the 3D view, and then the reconstruction tab, and adjust the contour value to the value you want to use it to create a shape mask. In this case, I would just use 0.6. So go back to the masking block and enter 0.6 for the threshold for binarizations. Okay, so we can launch it. Now the particles are successfully get rid of. We can create a movie frame refinement block. So let's go to the movie frame refinement. And again, they are pretty much the same, like same molecular weight, same radius. And we need to select new initial model from the previous block. The same thing. And then because we successfully clean the particle permanently, there's like underscore clean.par.bz2. We need to select this one. So we are now going to extract the bad particle during the downstream processing, right? And then we need to skip the refinement because the refinement here is without constraint. For tomography, we usually want to use the constraint. And for the constraint refinement tab, there is a movie frame refinement in the movie frame refinement block. Usually you need to select this option to get the trajectory, but I'm not going to do it here. The alignment here is pretty time consuming. So I just not select this options. So, and again, you can also apply the shape mask. Let's go ahead to create this block and how to get the mask. Now the masks are successfully generated. You can get the location of the mask by clicking the 3 line on the upper right of the block and show file system location and copy the file system location and go back to the movie frame refinement where you want to apply the shape mask and go to the refinement tab. Down in the bottoms, there's like a shape mask. Click on the this and copy the path you just copy. Hit enter and go to the freer line maps. And there's like a shape map. You can simply apply the shape map you just created for all the downstream processing or upstream process. And click on it. Everything should be all set. All right. So save it. Now we run the movie frame refinement block. Okay. So while we are waiting, we get to the movie frame refinement block in the pre-run model, pre-run here. So I'm going to demonstrate the post-processing, but essentially they are pretty much similar. The post-processing, you can select different kinds of B factor, and you can also apply the shape mask you just created. And the thing you will see is like the reconstruction, the sharpen reconstruction, on Mascade FSC and the Mascade FSC. And you can also download the map very easily to view the map in 3D. And I also want to mention the parameters. The parameter I just mentioned here for the movie frame refinement, we are not to do. Usually movie frame refinement, this one, you need to select the movie frame refinement, and down to the bottom, you should see there are 2 options, like regularized translation. It will allow you to regularize the noisy trajectory, and also apply some sigma values to make this the trajectory more smooth, or make the trajectory of the neighboring particle look similar, like two level of the regularization. And go to the exposure weighting. We do have the parameter for the frame fractions and the weight transition I introduced yesterday. Like these two values will adjust or control the weights used for the reconstructions. Right, and this process take quite long. I think I pretty much cover everything. And yeah, I also want to mention, we only have few blocks here, but you see there's like a lot of blocks in the workflow, in the pre-run workflow, but you actually don't need to do that. You can, like when we zoom in, you see they're like the same types of block connected to each other. You can combine them into one. So how to do that? You can, like, for example, I click on this to create a new particle refinement block. And if you want to do the same thing, that's just, for example, you do one iterations for reference space refinement by clicking the refinement particle refinement job options, and then go to the refinement tab. You do it for one iterations, starting from 2. So you do it, and then you get some result. I'm not going to run it, but you get some result, I assume. And then if you want to change something, you don't need to create a new blocks. You can instead change the parameter accordingly. Now we want to refine the two-series alignment parameter, for example, and click on that options, and then adjust the last iteration to 3. So it will run additional iterations in the existing block, in the same block. So you don't really need to create a new block like the pre-run workflow like this. And same for all the following block where you see the two identical block are connected to each other. Right. So, okay. And I also want to demonstrate, you can go back to the dashboard in the pre-run workflow, and we have the 10304, which is to purify ribosomes, and go into that, where we have the 3D classification in the last step. And the 3D classification can be done in particle refinement block. And I just want to point out, we have multiple classes. If you're doing 3D classification, you should see these two new tabs showing up in the particle refinement block. One is class view. As I mentioned yesterday, you can go back to the previous iteration very easily. Now we have 20 iteration in this case, and now we have 8 classes, and this class only has the large unit. We can disable it or hide them all and select the class you want to see. Anything you can do. And also for the same for resolution, FSC, and occupancy. And you go to the movie, you can adjust the order of each classes very easily and make movies to see the motions very easily. Yeah. And if the E3D view, you can compare the classes from different iteration very easily. Now you can see there's a lot of classes from all kinds of iterations. That's the things I want to highlight. Okay, while we are still waiting, yeah, I'm going to demonstrate RTIX. So what is RTIX? RTIX is if once you have the reconstructions, you want to map it back to the tomograms to see where the particle are oriented after the alignment, and to see whether to see the distribution of the particle or your proteins in the tomograms. So what you need is the tomogram, downsample tomograms, and the map and the alignment parameter, which is in the star file. So I'm just go ahead to download the 3 material for the RTIX. First will be the downsample tomograms. Go to the pre-processing block and go to the reconstruction tab, and you can see the rec file. Downloaded it. Should download the tomogram is downsampling tomograms, and then go back to the dashboard of the project. And let's say if I want to download the map from this panel, from the reference space refinement, go to the metadata, and then let's see. We are going to use tail series number 1. So search the tail series number, which is the name of the tail series, and select it, and you can download the orientation for this tail series, the orientation of the particles for this tail series. And then finally, we need a map. So go to the reconstruction, and we can download the cropped map. That's all we need for the RGIX. Okay, well, we are still waiting. I'm just go ahead to open the Chimera X. I make it bigger. So first thing you need to do is you have to open the tomogram we just downloaded, which is ends with .rec. Go ahead to open it, and then we need to run the 2 options to command to convert the handiness and the convention of the tomogram to match to the star file, the orientation to match the 2 coordinates. So I'm just go ahead to run the 2 options, and this will be in the RDIX, the 2 commands. First, you need to humate run the 2 options. They are also in our tutorial, so you can go look at it from in our tutorial to change the models, and then flip the z-axis, right? So you will create like 2 new maps. We only need the last one, so we can go ahead to cancel the first 2. So once you have the tomograms, go to the RTX tabs and launch it. Right, so there's like a new panel. First, we need to add the tomograms. You simply just click it here, and this is the tomogram we have. Simply click add it, and we have to adjust the pixel size here in tomograms. And remember, this number is wrong. You have to the binning factor you choose is based on the binning factor you use in the pre-processing block. Go to the tomogram reconstruction, and this is the binning factor. And the original pixel size is 1.35. You have to use 1.35 times 8, which is 10.8, and click apply. Okay, and then the second one is particle list. Open the list, which is the star file you just download. This contains the particle orientations. Right, so you have the particle orientations, and the pixel size here is also wrong. Go to the select and manuals. The pixel size here is original pixel size 1.35. And now you can see it match it. So you can get the coordinates right for all the particles. And lastly would be the maps you just downloaded, and go to this open geomodels, download the crop map you just downloaded, which is _crop.mrc. And then go back to the RTIX option, go to the visualization tab, and there's like use model, only one crop and map, and attach the model. So now you can see the reconstruction you obtain from the refinement can simply apply or map it back to the tomograms. You can simply adjust the threshold for all the maps. And if you really want to see whether or not the particle are oriented correctly or aligned correctly, you can go to the color map, and based on the likelihood contribution, which is essentially the score of the alignments, to see how they are oriented, whether they are correctly aligned, or some particle are like not properly aligned. You can see it in this diagram pretty well. And each reconstruction represents one particle. All right, that's everything about RDX. So let me just go ahead to close it. Now, okay, the movie frame refinement is still running, and I'm going to demonstrate the build file. What is build file? You can kind of have the better idea. This also offered in the Chimera. You can download it from the refinement, and then there's like a build file. You can simply download it from the particle refinement block. And you have to download the full size map in order to see the build file. The build file essentially it will give you the distribution of the orientation of the particle in 3D. Okay, so we also need to open it in Chimera. So I just go ahead to click on Chimera and then open the map. You just download it, not the crop one, the full size one, which is this one. And then open it, open the build file. You just download it. Now you can see because that it has the C6 symmetry, but you can get a better idea how the particle are oriented for this data sets by seeing the distribution of the orientation for the data sets. It's pretty simple things to do. All right, we are pretty much cover everything, but we are still waiting. I will just go ahead to show you how to do the post process. Usually we should do it after we are done with the movie frame refinement, but you can still create a new map. And the only thing you need to do to provide is the half map, the first half map, and it will detect the second half map automatically. And then the shape mask, same as before, you can get the location of the shape mask by copying the location of the shape mask and then simply apply it to the post-processing. Okay. And then there's like several options like low pass filtering and the B factor. I'm just go ahead to use -50, for example. And you can also invert the handedness if you want. And click save. And now, it's almost done. And yeah, I think I pretty much cover everything. So yeah, you can go ahead to ask questions.
Yes, we have a couple minutes for questions. I guess there is one here that says, how did you decide what symmetry to enter?
How do I? In this case, we already know this is C6 symmetry, but usually you don't want to turn it on at the beginning because it might introduce some bias. For example, if you are processing ribosome and you don't know anything about it, but you apply C6 symmetry on it, you got nothing useful. So usually we don't want to select, we use C1 symmetry, which is no symmetry. And then once you have the reconstruction, maybe using reference-based refinement, or if ab initio, you turn on or you select a different symmetry in the downstream processing. Hopefully that answered the questions.
Yes. There is another, we have run out of time, but maybe if you can quickly address, somebody's asking, what is the region-based refinement? Maybe which, I guess we explained a little bit about yesterday, but maybe just go over that one more time.
Yeah. What is region-based refinement? So let's demonstrate using the atomogram. So during the data acquisition, the particle may not move all together because of the local region. For example, upper right regions, they move to the right, or for the bottom left region, they move to the left. So we need to have additional parameters to describe the local motions. So how we did it is we divide the tomogram into several patches or several regions in X and Y and Z dimensions. So that's why you see 3 values for in the region-based refinement to divide them into different patches so that we can have more parameters to describe the local motions. Hopefully that answers questions.
Yeah, okay, that's great. So we're out of time, but I was just curious if the reconstruction from the frame is probably almost done.
Oh, I want to highlight, you can go back to the dashboard and simply click on the project we just created, and there's like a size. Now we only occupied about 30 gigabytes, which is pretty lightweighted. Also want to highlight the scalability and the last footprint, small footprint of our computing data processing framework. Right. Any questions?
Yeah, I think maybe it would be useful to just show the reconstruction once you get it. Maybe from the logs you can highlight, what are just to give people a sense of, what this reconstruction from frames, how many images we're looking at, and so forth.
Yeah. So this is the number of this dataset has 2 tilt series only. And for this amount of tilted images and the frames we have this number of particle frames, which is pretty many. Right. Anything else?
Let me see. Yeah, there's I guess somebody's asking again, what is the meaning of the score?
Oh,
and whether they can be compared across different tilt series.
you can not compare. Usually cannot compare different tilt series. So first, the first questions. For each particle, you have to think of it has multiple tilted projections. So to get the mean score or to get the per particle score, we kind of, for each tilted projection, you have a score. We average all the score to get the per particle score. That is the per particle score, I mean. And each data point in this histogram is the one per particle score. And because you use different defocus, they may not have the same score from tilt series to tilt series. If they are using the same defocus, you might see the same histogram or similar shapes of the histograms. But if you're like the data sets are like tilt series are too different, they may not have the same quality and you will not see the same histogram from tilt series to tilt series.
Okay, great. So I think if the run is done, we can show the results and then transition to the last session of the practical, which is going to be the live processing.
Okay, so now it's done, and it has this number of the particle frames, and then we can go ahead to click on the first map from the previous block and simply click on it and run it. Now you will see the post-processing, right? And yeah, you can still see the reconstructions and everything. And if you want to know how much space it occupies, go back to the dashboard and click on the project, and it will tell you how much space it occupies. Okay. Don't think we need to wait until it's done because I already showed that in the pre-run workflow.
Okay, yeah, then that's fine. We can transition now to the next one. Thank you, Chanfu.
Thank you.